Hello students, welcome to Quick Solutions All India AIATS Test Series JEE Main 2020 Test 3 Physics. Let's go to question number 1. Question 1 says, a current of 5 ampere flows in a long straight wire with cross section of the form of a thin half ring of radius r equal to 10 centimeter. See figure. The magnitude of magnetic field at point O is. Well, we have to find magnetic field here, and we will use the result B is equal to mu naught I by 2 pi r, which is actually the magnetic field due to a straight thin current which is infinitely long at distance r from that thin current. In this particular question, we will divide this cross section into small elements. And to do that, I draw a vertical line passing through O. This is the reference line, and I draw two radii at angle theta with this line and angle theta plus d theta with this line. So that means I draw these two radii. This angle is d theta. Now we have a small length enclosed, and that length is equal to r d theta using geometry. So this is our element. We will find magnetic field at O due to this element, and we find the current enclosed within this. That current, we can call it Di, is equal to, we can apply the unitary method. So the total current is I spread over a length of pi r, and so for length r d theta, the current enclosed is Di is equal to I by pi r into r d theta, which is simply I d theta upon pi. The magnetic field at O due to this current alone, we shall of course use this result, in which we shall replace capital I by Di and small r by capital R, and then we are going to get dB is equal to mu naught di is I d theta by pi by 2 pi r, which we can simplify as mu naught I d theta divided by 2 pi square r. Now what's the direction of this field? Well, if we assume that the current is coming outward through this wire, then using the right hand rule, the magnetic field will be perpendicular to this line. So let's call it, this is your dB, and we can see that this dB can be resolved into two components. One component is in this direction, the other component in this direction. We can call this as the x-axis, and let's call this as the y-axis in this particular case, and this is our dB, as I told you. Now we can see that this plus this is 90 degree, and this plus this is also 90 degree. That means this angle is again theta. So the x component of magnetic field dB, which is dBx, is equal to dB cos theta. Now if we analyze further, we can see that for different elements, for example for element here, the magnetic field will be directed like this, and if we analyze further, we can see that by symmetry the components along y-axis will cancel themselves, and we will have a net magnetic field in the direction of x-axis that I have drawn. So that means by simply integrating dBx, we are going to get the net field, and dBx in our case is dB cos theta, which is again, if I put the value of dB that we got here as mu naught I by 2 pi square r cos theta d theta. Let's integrate it, and the limit of theta of course will go from minus pi by 2 at this point to plus pi by 2. So I put the limits as minus pi by 2 to plus pi by 2, and if we simply integrate, we are going to get mu naught I by 2 pi square r into sine theta, and if I put the limits, it is sine pi by 2 minus sine minus pi by 2, that means again sine pi by 2, which again simplifies further to, this will become 2, so it is simply mu naught I by pi square r. Now we have the result. Let's put the values that's been given to us. I is 5 ampere and r is 10 centimeter. The value of mu naught we know is 4 pi into 10 to the power minus 7 SI units. The value of I is 5 ampere, so I put that value, and then I get pi square, and r is 10 centimeter, which is 0.1 meter. So 1 pi cancels out. We have 20 into 10 to the power minus 6, that means 2 into 10 to the power minus 5 divided by pi in SI units, or that is simply Tesla. Let's look at the options. This is clearly matching with option 2. So option 2 is correct for question number 1. We can now go to the next question. Question 2 says, the force vector acting on a unit length of a thin wire carrying current I, see figure at point O, is. So we have been given this figure. There's a loop. It's like a semicircular loop carrying current I, and the XY axis have been given to us. We are supposed to find the force vector acting on a unit length of a thin wire at point O. So at the center, what's the force acting on a unit length? That is what we are supposed to find. So first, to find the magnetic force, we first find the magnetic field at point O. The magnetic field at point O is B, let's call it BO. We can see that the field due to this segment will be 0, and due to the semicircular part, the curved part, the magnetic field is mu naught I by 4r, and the direction of this magnetic field is inward, that means it's along minus k cap. So this is the magnetic field vector at point O. Now let's take a small segment of length dl, so that the dl vector in our case is dl minus I cap, because it's along the negative x-axis. And so the magnetic force on this element will be I into dl cross B. That's a standard expression for the magnetic force on a current carrying wire. And if I put the values, well, I is I, and as I said, dl is dl into minus I cap cross mu naught I divided by 4r into minus k cap. We simplify it further. We get this df vector as I by 4r, and then mu naught I into dl, and if we carry the cross product, I cap cross k cap will be minus j cap, and this minus into minus is 1, so this is minus j cap is the direction of this force. This is the magnetic force on a small element of length dl at point O. We are supposed to find the force vector on a unit length, so that means we are interested in finding df by dl. We divide the force by this length, and the expression that we get is mu naught I square by 4r minus j cap. If we look at the options, this is clearly matching with option 4. So option 4 is correct for question 2. Let's go to the next question now. Question 3 says, A charged particle is moving with a uniform velocity of 5 into 10 to the power 5 meter per second along the y-axis under the action of a magnetic field along z-axis and an electric field of magnitude 10 to the power 4 Newton per Coulomb along the negative x-axis. If the electric field is switched off, the charged particle starts moving in a circle. The radius of the circle is close to, and it's given Q by M ratio of the particle is 5 into 10 to the power 7 Coulomb per kg. And we have these four options given. Well, what the question is saying is that the particle is moving with a uniform velocity whose magnitude is given along y-axis under the action of both a magnetic field along z-axis and an electric field of 10 to the power 4 Newton per Coulomb along the negative x-axis. So the particle is moving with uniform velocity. That means the resultant of magnetic force and the electric force on the particle is 0. Later on, the electric field is switched off, and after that the particle starts moving in a circle. We are supposed to find the radius of that circle. Well, we clearly have, the Lorentz force expression is Q into E plus V cross B, and in this case this expression is 0, which means we can straight away say that V cross B is minus E. And what is minus E vector? Well, the magnitude is 10 to the power 4 Newton per Coulomb, and E has direction along negative x-axis. So that means minus E is 10 to the power 4 I cap, and of course the unit will be Newton per Coulomb. That's the direction of V cross B, and which means the magnitude of magnetic force on the particle, which is mod of Q into V cross B, assuming Q is positive, is Q into 10 to the power 4 SI units. Okay. Now once the field is switched off, this force will provide the centripetal force, and that means it is equal to mv square by r. And so the expression for r, the radius of the circular path, is mv square by q into 10 to the power 4. Now from here on it's pretty straightforward. We have the value of v, and q by m also is given to us. We simply substitute the value of q by m, which is 5 into 10 to the power 7 SI units. The v square will be 5 into 10 to the power 5 whole square, and of course there is 10 to the power 4 here. So this, if we simplify, we shall get it as 0.5 meter, which matches with option 4. So option 4 is correct for this question. Let's now move on to the next question. Question 4 says a magnetic dipole is acted upon by two magnetic fields which are inclined to each other at angle theta. One of the fields has a magnitude of 20 millitesla. The dipole attains stable equilibrium at an angle of 37 degree with this field. If the magnitude of the other field is 15 millitesla, the angle theta is nearly. Okay, so this question is based on the torque acting on a magnetic dipole in a uniform magnetic field. Now, in this particular question, the dipole is in equilibrium under the action of torque applied by two magnetic fields. So if I call the magnetic fields as vector B1 and B2 respectively, then I have the expression, and also let's assume that the magnetic dipole is vector M. Then we have M cross B1 plus M cross B2 is 0, and which further implies that M cross B1 plus B2 vector is 0. Well, we know that B1 and B2 are non-zero and they are not equal in magnitude. So it clearly means that the resultant of B1 and B2 is either along vector M or opposite to vector M. The angle between this vector and this vector could either be 0 or 180 degree, because it's clear that vector B1 plus B2 cannot be 0 because their magnitudes are different. So that being the case, let's also try and draw the situation here. Suppose this is vector M, and one of the angles, the angle between vector M and vector B1 is 37 degree. So let's say this is our vector B1 and this angle is 37 degree. This magnitude is 20 millitesla, and M cross B, we can see that is in anti-clockwise sense, right? Is coming outward. So the other field B2 must provide a clockwise torque. So that means we can imagine B2 to be somewhere here, is directed somewhat like this. So if the torque by B1 is in the anti-clockwise sense, the torque by B2 is in the clockwise sense. Now this magnitude is 20 millitesla, this magnitude is 15 millitesla. Let's say this angle is theta. Then what we have is, we just equate the magnitudes of the two torques, and what we get is M into 20 millitesla, and sine 37 degree is close to 3 by 5 is equal to M into 15 into sine. Well, we can't say call it theta because theta is the angle between B1 and B2. So we can call it, let's say, theta dash. So M into 15 into sine theta dash, which gives us sine theta dash equal to 20 into 3 by 5 into 15, which is simply 4 by 5, or we know this value of theta dash can be taken as 53 degree. So this implies angle theta, which is 37 degree plus theta dash, and that will be equal to 90 degree. Let's look at the options. Well, option 4 clearly matches with our answer. So option 4 is correct. We can now go on to the next question. Question 5 says, the magnetic susceptibility of a certain material is 600. This material belongs to the class. Option 1 says paramagnetic, option 2 says diamagnetic, option 3 says ferromagnetic, and option 4 says ferroelectric. Well, it's a straightforward question, fact-based. We know this kind of high values of susceptibility is observed by ferromagnetic materials. So the answer is option 3. Let's go on to the next question now.